Hello, everyone. It's a great pleasure to be here back at EPFL, at the place I consider my academic home. Today, I'm going to talk about AI, or artificial intelligence-powered databases, as a vehicle for fast-tracking insight discovery from large databases. So why do we talk about large databases? Well, many of us know that data is increasing exponentially, and every year we generate the same amount of data we have generated when we sum up all the years throughout that year. Now, that's all great. We have large amount of data, but why does it matter? It matters because businesses around the world are realizing the power this data brings and the potential to innovate, to optimize processes, and bring competitive advantages. And as The Economist nicely put it, the world's most valuable resource is no longer oil, but data. Considering that, many enterprises around the world are building fit-for-purpose platforms with the main purpose to drive business innovation and differentiations by focusing on compressing time to value of insights from complex data sets. So this is quite interesting, right? We recognize the potential that data brings, and we all know that insights are hidden in the data. But how do we uncover these insights? And when we say uncover insights, typically in the database language, we use the term data exploration, which is really the process of mining data to uncover these patterns. Now, this process is quite challenging from the practical perspective, and finding an interesting insights more frequently than not is actually like finding a needle in a haystack. So I'm here showing a recent example published in the ABC News, which is an Australian news outlet, where the brightest and fastest growing black hole was accidentally discovered by an astronomy student. And the emphasis here is on the word accidentally. The telescope was set in motion in Australia in the early 2000s. It generated large amounts of data more than 20 years ago, and scientists all over the world have mined this data set, yet somehow they all missed it. And this really pinpoints to this problem of how hard it is to discover the insight. Now, how do we discover the insights with databases? And this is now database one-on-one, if you wish, for those of you who are joining us who are not of database background. So in a typical scenario, a user is going to issue a query to a database. And that query is typically posed in the form of SQL. So in this particular query, we ask database something. The database decides on the best way to execute that particular query, and then it returns the results. And this is the process we call querying. Now, in a typical scenario, the user will then ask follow-up query, and there are several queries that we keep asking, analyzing data, and leading us towards interesting insights. And on the right-hand side, I'm showing this timeline, how the time goes when we query. Now, before we are able to query data, we need to prepare database for analysis in the process we'll call tuning. And this is the process that makes sure that data retrieval is as fast as possible. And when we talk about getting the value from the data, the big focus the databases have is on minimizing the data to insight time, which is really the duration from the time data is available until we can extract useful insights. And given the benefits that new insights bring, typically nowadays the database goal is actually to minimize this data to insight time. Now, how do we do that with databases? We do it with a process called physical database design or performance tuning. So in a typical scenario, a database administrator observes the workload and uses the workload to create a set of physical design structures that speed up the retrieval of the observed workload. So these physical design structures could be indices, B+ trees, materialized views, which are caches or summaries of past results, so aggregated data and past query results, or even through caching or prefetching, where we bring raw data ahead of time in main memory to speed up data retrieval. Now, this is a traditional process. However, data exploration use cases are in stark contrast with the typical workflow. First, because the users of the databases are domain experts, but not necessarily database experts. So they could be healthcare providers, astronomers, biologists, right? They have a lot of knowledge in their domain of expertise, but they don't necessarily know how to tune the database systems. And moreover, the type of analysis they run is actually what we call ad hoc or unpredictable exploration, where the workload, which is the set of queries the users will run, is unknown ahead of time. So how do we then minimize data to insight time in data exploration? Well, the answer is it's quite hard. First of all, because the observed workload is non-existent, and also because we frequently don't have database knowledge. And this has led me to the topic of today's talk, where we have recognized this gap, and for many use cases that exhibit data exploration properties, being from sciences, from businesses, from healthcare, we have seen that traditional databases are not fit for purpose of servicing those use cases, and more often than not, users opt to use custom-made solutions rather than leveraging 40 years of database development. In this talk, I am offering a glimpse of a potential solution, which are AI-driven databases that can automatically learn from user interactions with the database to optimize its performance. And this brings me to the outline of my talk. So first, we're going to talk about how we can select those physical design structures to tune performance of the unknown and ad hoc workloads. Then we're going to dive under the hood and look at the layout of these physical design structures. In typical scenario, we would consider traditional indices, B+ trees or hash indices. However, the layout of these structures could be quite different. And this is something that we are going to examine in the second part of the talk. And finally, in the last part of the talk, I am going to discuss some of the prefetching techniques we have developed to support unpredictable and ad hoc data exploration use cases. So let's start. So why do we talk about physical design tuning in the first place? Well, because this process is quite challenging, and this slide shows why. So In this slide, I'm showing the impact of performance tuning of a mature commercial database system when running a publicly available benchmark TPC-H. And to boost performance of the workload, we have invoked the physical design tool shipped as part of the commercial system to tune performance and propose a set of indices estimated to boost performance of this workload. And what I'm plotting is individual query results after tuning normalized by the original execution time. So that means the bars below 1 denote that performance got improved, and bars above 1 imply that performance got degraded. And as you can see, although performance of some queries got improved, there are quite a few cases where performance got degraded after the tuning. So what happened there? So let's look at the physical design tuning process under the hood. So in a typical scenario, the database administrator provides a representative workload to the physical design tool. The task of the physical design tool is then to propose recommended physical design configuration estimated to boost performance of this workload. Now, how the physical design tool does that, it communicates with the query optimizer of the databases, or which is the critical component or the brain of databases, which decides how each individual query is going to be executed. So how does this communication look like? They communicate through something called a VATIF interface, where the physical design tool asks the optimizer what would be the benefit of a particular physical design structure for the given query, so for the given workload. So the physical design tool can ask, for instance, what if I had this index? And the optimizer said the estimated benefit is X. And what if I had another index? And this conversation, if you will, continues until the physical design tool has sufficient information to propose the configuration estimated to be the best. Now, the issue in this pipeline is actually twofold. First, in data exploration use cases, workloads are unknown and ad hoc and unpredictable. And second, even in the cases when we know workloads ahead of time, this estimated benefit frequently can be wrong. And this is exactly what has happened in the previous case, in the previous slide that I used as a motivating example. Even though we had perfectly known workload that was repetitive and we knew exactly which queries are going to be run, the optimizer still misled the physical design tool about the benefit of several physical design structures. So this is really a broken pipeline, and the research community has recognized this problem and examined several different approaches to performance tuning, leveraging machine learning algorithms as a way of learning through observation rather than analytical modeling. And this area has quite blossomed in the last couple of years. And even if you type on Google Scholar, for instance, database tuning with machine learning, you will see 500,000 hits already, with many papers quite heavily cited, such as this work from Paolo. So I can't quite do justice to the research community and mention all relevant papers. So I do encourage you to do the same exercise like I did, but it is the area that is gaining a lot of interest recently. In my group, we have examined multi-arm bandits for physical design tuning. Now, before I start discussing physical design tuning with the bandits, I want to take some time to explain how the bandit algorithms work. And I will use this image of slot machines because this is what we frequently see in the literature. So imagine that you have a set of slot machines and our goal is obviously to become richer, although I don't suggest gambling, definitely. So what we can do, we can put a coin in a particular machine and see what happens. The machine can give us money back. Maybe for one coin, we get 2 coins. Maybe it just gets our money and doesn't let us do anything. Now, if we got, for instance, 2 coins back, we could continue to exploit this machine because every time I get a coin in, I get 2 back. Or at some point, I can start thinking, hey, well, there's many more machines. Maybe I should explore some of the other machines. Maybe they will give me more than just 2 coins. And this is the concept of exploration. Now, I have this dilemma between exploiting the choices I have seen how they work and exploring new choices. And this is really this is really where multi-arm bandits algorithms shine as a set of algorithms that offer a solution to the exploration and exploitation dilemma, where the task is to find a sequence of arms or choices we make to maximize the cumulative reward. And there are many bandit algorithms out there, but of particular interest to us was C-square UCB, and I'm going to talk about that in the next slide. So let's see how we can tune indices by leveraging multi-arm bandits. So we have the same image we have seen before, but now slightly modified. So the first modification is that bandits do not require observed workload to be given ahead of time. Instead, they observe workload as in monitoring which queries are coming. In this black box here, what is happening is that multi-arm bandits perform continuous learning where they are trying different choices, arms in the bandit lingo, which is really index choices. They observe reward and they continue this process of recommending indices, observing the workload continuously. Throughout this process, they completely ignore the optimizer due to risk of received misestimates. So it's like continuous learning through observation. Now, there are several algorithms, as I mentioned, but why we have picked C-square UCB is due to several properties they offer. So UCB stands for upper confidence bound, which guarantees convergence to optimal policy in hindsight, which is really strong indication of the algorithm effectiveness. The other 2 C's, first C stands for context. So contextual bandits allow us to learn the benefit of particular choices or arms even without pooling them, without trying them, through the context attached to the arms where we share the knowledge so we can learn the benefit even without trying them. And the last C stands for the combinatorial aspect, where we can pool a set of arms, a set of choices at once and observe the reward and distribute it through the concept of mini arms to individual choices. So what we ultimately have is really algorithm that provides safety theoretical guarantees with fast convergence. So how does that work in practice? More detail is provided in our ICD paper, But at a very high level, how the concept works is every time a query arrives, and it's shown here on the left-hand side, it is sent to the bandit tuner that then generates or identifies arms, different index choices that would benefit particular query. The learner then opts for a particular configuration, in this particular case, index 6, that gets materialized, query gets executed, and then we observe the reward and feed that information back into the learner that captures everything in terms of the context and reward. So we can learn that, for instance, the particular index brought 10 seconds of gain in terms of query execution. It took 20 seconds to create it, and the index occupied 30 megabytes inside. So all of this is fed back to the learner that adjusts the context weights and inform the next decision making. So what we have here is really an example of autonomous tuning, continuous tuning without user input. Okay, so let's see how does that work in practice. Here we have run exactly the same experiment that I have run before, but now using the bandit tuner as opposed to commercial tuning tool. And you can see that now performance obviously gets substantially improved, but also there are no cases of performance degradation because we learn through observation, and therefore we learn the actual benefit of individual data structures. And we have run experiments across a range of different data sets and different workload types. And I'm here showing just a summary. So you have two sets of graphs. On the left-hand side, we have a static case, which is really the perfect use case for physical database, for commercial physical design tool that we compare against, colored in orange, where workloads are repetitive. And on the right-hand side, we have the more interesting use case, which is the data exploration use case, where queries are changing over time. And we compare the physical design tool against the map multi-embedded solution that's colored in gray. On the y-axis, I show the total workload time, which involves the entire process of tuning, creating physical design structures, as well as workload execution. And there are two interesting points to note here. First, that multi-arm bandits work quite well for the traditionally challenging use cases, such as data with skew, which is this case of TPCH workload, or when queries are a little bit more complex, which is TPCDS workload. And obviously, when queries are unknown ahead of time, then we get substantial benefit over the traditional solutions. Okay, so this was all great. We were quite encouraged with the initial early results and success of the bandits, and we started thinking about more complicated use case where we consider different physical design structures, such as indices plus views. And we used exactly the same architecture, and I have to say failed miserably. Because the design space became too large and it was complex to design effective context. The context became too long, which then led to slow learning, and overall we didn't have a competitive solution anymore. So as a result, we came up with hierarchical multi-arm bandits, as a solution for integrated physical design tuning when we have a larger space of options. So how does that work in a nutshell? We have two layers of bandits. So it's a hierarchy of bandits, where at the L1 level, we have individual bandits that tune individual tables looking for beneficial indices. We also have one bandit that considers materialized views. So as a result of these individual bandits, we get locally, if you wish, optimal solutions per table. Those arms, those choices are then fed into the L2 bandit, then makes a global decision amongst these, which data structure should be materialized. And it's an example of how divide and conquer actually helps us reach this global optimality while still having an integrated solution where the interplay between different data structures is actually incorporated at the L2 bandit level. So how does that work in practice? We have run many more experiments in our VLDB paper, but in a nutshell, we observed similar or even better results now with integrated physical design that has indices and materialized view. So this solution consistently outperformed the commercial physical design tool that we have compared against. So this was really great, and we started exploring the potential of bandits, but then considered a traditionally challenging use case of performance tuning, which is HTAP workload, where we have a combination of transactions and analytical queries. And these are really the cases that are stumbling blocks for traditional commercial tools, because analytical modeling becomes very, very challenging. It is hard to capture the information that are essentially happening at runtime, because a particular data structure can be beneficial for retrieval. However, it can also incur additional maintenance when we are adding or updating data. So it helps to some extent, but also hurts performance. What we have done for this work, we have also introduced the context of focus updates, which is really the new flavor of bandit algorithms that actually have better regret bounds, where we can split the weight vector in small portions, where part of it captures the gain and the other part captures the overhead. And in that way, we can independently update and learn them, which really leads to faster convergence. All right, so in summary, we have spoken about hierarchical bandits as a lightweight solution for integrated physical design tuning. To our knowledge, this was the first learned solution that really worked in this combined space of indices and materialized views. And what was interesting is that the tool was able to deal with traditional stumbling blocks of performance tuning optimization, such as relying on the optimizer misestimates or dealing with unpredictable or HTAP workloads. So we have continued this work in several directions and also have several more theoretical papers in the bandit theory for those of interest. For instance, looking at the warm-up process of the bandits, where we address the cold start problem of the bandits, or where we looked at bandits under different reward scaling. For instance, if we observe rewards in one unit, but then the actual execution is in a different unit set. For instance, when we learn something in the optimizer artificial cost unit, but the actual execution is happening in runtime, and we measure actual physical time. So there are some solutions how we can address that as well. And for those who are interested, I would like to point you to those two ICDM papers. All right, so far we have discussed how to choose which physical design structures to create. Now we are going to investigate how we can decide on the layout or look, if you wish, of these physical design structures. So in a traditional scenario, an index is typically a B+3 index, and I'm showing a small representation of a B+3 index here, where we have the root node of the index, and then we have different nodes, different inner nodes that we use for searching. Finally, in the leaf nodes, data is sorted by a particular key, and how the search works. When we search for a particular key, for instance, age equal 18, we would traverse the B+3, we would find the first record in the leaves where we have the key with the value of 18, and then we follow the pointer to bring that data to the user. And if we need more, if we have more users, we'll just continue this process of grabbing 18 and jumping there. So this is how a traditional B+3 index works. Now, in the recent years, there is this new area of learned indices, where the idea is to replace this big, large B+3 index with a small learned model that learns the distribution of the data. So how then the querying works? For the given key, the model will simply spit out the position where the key resides. Now, why this area has become so interesting? Due to potential to replace these quite large B+3 indices, because remember, those are auxiliary data structures that we build on top of our already big databases. We have a potential to replace them with smaller, much smaller learned models that could be linear regression model or something more piecewise linear regression model, something quite small that is then faster to actually query. And again, this area has become quite prominent with the appearance of the paper from Kraska, the case for learned index structures, published a couple of years back. And again, if you do the same exercise I have done, where you just type on Google Scholar learned index, you will see quite a few hits right now, reaching 10 million already. So this was really an interesting area, and there was a lot of work in proposing different learned indices. What we have done in my group, we have investigated how ready those learned models are for on-disk placement, because many databases nowadays are still storing their data on disk due to sheer volume, and we cannot always afford that all indices stay in memory. So what we have done, we have started by analyzing state-of-the-art learned index models listed here, Fitting3, PGM, Alex, and Lip, and we have modified them to allow on-disk placement. And then we have run an extensive experimental evaluation comparing them against B+3 across a range of different data sets and different workload types. So we have examined everything from the lookup only, one search only workloads to the write heavy, read heavy combinations of different and balanced workloads that have the combination of both insertions and queries. And there are many more experimental results in the paper, but this one summarizes really the main findings. And it's a spider chart that I have to demystify. So the spider chart is normalized by the best choice. So we're looking at the round of 1, and essentially in this particular case, when we look at, let's say, bright heavy workload, we have B+3 is the best. Balanced, again, B+3 is the best. And actually, across a range of different data sets, we have observed that lookup only workloads, where we look for the point query for just particular keys, the only use case where learned indices could still outperform traditional B+3s when we allow disk placement. So this was quite surprising to us, and we have investigated what has happened and where do these overheads come from. And we have again produced many more results, but this slide summarizes the main findings. So the first one is once we allow the disk placement and everything is organized in terms of disk pages, the actual learned indices produce trees that are much higher than the traditional tree, B+3. And this is shown in the table on the left-hand side, where we capture the number of blocks for the lookup and for the scan. And you can see in particular for the scan, where we search for several records rather than several range of values rather than one, you can see that B+3 actually touches fewer I/O operations or blocks compared to the learned indices. And the other big issue we have observed is that most learned indices suffer from large insertion overheads, mostly related to the statistics update, modification of different models, structure modification operations, and in the process of inserting data. So what we have then done, we have investigating all the overheads and proposed a set of design principles for effective on-disk learned indices, and they're listed here, where in order to tackle the two challenges, first we need to focus on reducing the tree height of the index. Model-based operations should be lightweight and effective. We need to make lightweight structure modification operations, meaning that when we start inserting data, the model updates and everything needs to be much more lightweight. And also we should focus on improving scan performance, because there are many workloads that scan ranges rather than an individual point lookup. And obviously, supporting duplicate keys is important, and some indices would still struggle with that to cater for it effectively once data is stored on disk. So this is how the proposed solution, OLID, looks like in a nutshell, and I'm gonna demystify this in a bit. So we have the metadata node, which is sort of similar as a root node, which is where the search starts, and then we have a number of inner nodes that are actually heterogeneous in nature, and then we have leaf trees that actually resembles the layout of the B+ trees. So in a nutshell, really, the OLID layout leverages the best of both worlds. It uses the benefits of the B+ trees, but also of the learned models. Let's go node by node or layer by layer. And let's start with the leaf node, because that is the simplest one. So in the leaf, we have the layer that really resembles the B+ tree. So we have nodes that are equal to block sizes and then different data slots to store the index values. We have empty slots to allow additional placement of additional records whenever insertion happens. And then we have pointers between siblings so that we can move left and right when we are examining different ranges. What's the benefit of this design? The benefit is that we really have efficient scan operations. We can easily move through the keys left and right once we reach the leaves. And also, through our profiling, we have observed that SMO operations bring the biggest overhead in the leaf level, and by removing them from the leaf, we actually reduce this overhead substantially. Now, in terms of the inner nodes, they are heterogeneous in nature. So the first one here that I'm showing is the mixed inner node, where we can hold different types. We have different slots, we can store data, we can store pointers to lower levels, and also we can store models where we use a model to determine which slot is going to be accessed next. We also have packed inner nodes that hold pointers to the leaf node and a lot of data as well. And what are the benefits, right? You might ask, if we have the leaf nodes that resembles the index, and then inner nodes that again a little bit resemble index, where will the benefit come from? So the answer is the benefit comes from those inner layers because they are substantially smaller, right? The nodes would be bigger in size, but here we store the model that leverage data distribution, and we should, instead of packing every key in the inner nodes, we actually have the models and we know where to jump. We use model for the search and to determine which slot is going to be accessed next. So what happens practically is that these inner nodes are much smaller overall compared to B+3, and the height is also smaller compared to the B+3. Now, by leveraging a model-based operations, we have efficient search and insertion, and also the overhead of structure modification operation is reduced. So how does that work in practice? Here are the results, and many more results are provided in our ICD paper, but you can see that across different data sets and across different types of workloads, OLID, colored in brown, is consistently outperforming all other choices. This was an example of a learned index where we re-examined the layout of indices, combining the benefits of traditional B+3s and learned models to propose a solution that is robust across a range of workloads and different data sets. All right, so in the last couple of minutes, I'm gonna quickly mention our third line of work, which is on prefetching data ahead of time to speed retrieval, again in the case of unpredictable and ad hoc workloads. So I have already mentioned the importance of efficient and effective data exploration, and there are many use cases where it has been shown that query latency is critical to enabling how effectively we analyze data. So the latency above 0.5 seconds, essentially half a second, already has a huge impact, huge negative impact on how we generate hypotheses and questions and analysis. So there is a big emphasis on reducing this latency to be sub-second latency. And one of the tricks we can do is to do prefetching to support this interactivity. How does prefetching work in a nutshell? So in a typical scenario, when a user types a query, it is sent to the database server that decides on the number of blocks that are going to be accessed to answer that query. If those blocks are stored in the main memory cache, they're served directly from the cache, and this is something we call cache hit. And as a result, we get our responses quite quickly. However, if those blocks are not stored in the in-memory cache, we encounter something called a cache miss, and we need to go back to the disk and retrieve the data, which takes much longer. Now, prefetching is a process of leveraging past historical query data accesses to predict which block accesses are going to be accessed next and bring those blocks into cache ahead of time. Now, this sounds very simple in theory. In practice, it's not so easy to do it, especially when we consider arbitrary ad hoc SQL workloads where the next query can be literally anything. Past efforts have mostly focused on leveraging block addresses, so the numbers as the driver for a prediction of prefetching. So for instance, if we access block 1, 3, and then 5, the prefetcher would say, okay, next one is 7, right? But we've never leveraged the semantics, which is really the meaning of this data. And this is what we have tried to do in this line of work, where we have looked at prefetching as a time series forecasting problem, where we leverage actually data semantics, the meaning of the data, to learn the interdependency between queries users are asking and the data they are touching as a result. So this is the architecture we ended up with. And again, I'm going to demystify it in a bit. What we do is a three-step process. First, we encode all the blocks using autoencoders to capture the meaning of each block. Then we group sequence of blocks that are frequently accessed together into a notion of logical partition. And this is a continuous process that adapts and adjusts depending on how workload changes. And finally, once we have the encodings of the partitions and the encodings of queries, essentially which partitions they are touching, we feed that into prediction model that then decides on the number of partitions that are going to be accessed next, looking at the probability of their access. So let's consider the first task, which is block encoding. Now, blocks in principle can contain hundreds of values. And I have a simplistic example on the right-hand side where we have one block with 4 attributes and several records. And after invoking autoencoders, we end up with this vector embedding, which really says here what we have is mostly stars with some galaxies. Typically, all objects are small size. These are average values of the G and R, for instance. So this is what autoencoder distilled as the most interesting properties of this block. And then what we really have ultimately is classification problem, given the sequence of the last X query encodings, where we encode essentially all the blocks accessed by a query. The task is to predict next blocks. Now, for a large data set of a couple of millions of records, this really becomes a substantial number of labels. So to deal with this problem, the scalability issues, we have actually grouped blocks frequently accessed together into partitions. So we create affinity graph where we capture the connection between different blocks through those edges with weights attached to them, and then we perform graph partitioning on affinity graph. As a result, once we have the block in a partition, we do partition encoding or embedding, where we actually get a matrix of features because we can't really aggregate across different feature vectors from different tables, right? They might have different meanings, so we aggregate them at the level of a table, and then we end up with this matrix. And the same process happens for queries as well, right? Depending on which partitions queries touch, we actually do encodings and aggregate them so that we have that for each individual query. And then simply we feed that into the learner, which is in this case encoder decoder LSTM network. And on the right hand side, for instance, I show the input to the learner, which is just in this case passed to queries and their encodings. And to demystify, for instance, what the learner learned here is that it seems that we have been accessing partitions that mostly contain galaxies and very high G on average. So this is something that's going to be fed on in the model, and most likely proposed partitions would exhibit some of the similar properties. And how does that work in practice? In principle, it worked quite well. So CELEB, which is the algorithm we developed, achieved quite high hit ratio across the number of workloads we have tested. And also, we have seen that in all the cases we tested, the relative I/O time or the savings we got from prefetching, we managed to reduce I/O substantially compared to these state-of-the-art prefetchers. So overall, CELEB was an example of semantics-driven prefetching, where we have used the meaning of the data and interdependency between data and queries as a driver for learning and for predicting which sequence is going to be accessed next. All right, so this brings me to nearly the end of the talk. Just to summarize, today I spoke about AI-driven databases that automatically learn from user actions and the properties of the queries, data, and the hardware as a driver for learner to provide fast responses. And we have spoken about physical design tuning, about the area of learning indices and caching, all as different means of increasing query performance or reducing query response time. Now, where do we go from here? So there are several different problems we're considering in my lab currently. So how I see the AI-powered databases, I see them more as a co-pilot for insight discovery. So we are actually stepping away from databases as passive data retrieval providers, where the only emphasis is on producing results quickly, to actually being co-pilots that can advise and help users mine and find interesting insights buried in the data. And towards that end, there's several questions we have examined. For instance, what makes some data interesting? So there are different measures of interestingness that we consider. What's the notion of novelty, and how is that related to insight discovery? We are looking at whether we can predict user intent, both from the short-term perspective, but also from the end goal perspective, which is looking more into autonomy. And also we are investigating whether we can recommend queries that lead to insight, that guide users towards insight. This was all from me today. Thank you so much for listening, and I'm happy to take any questions. Given that you're unable to ask your questions now, feel free to reach out to me. My email address is here, my personal website, as well as the project website. Thank you so much, and until the next time.